Good morning, physics students. This lecture is the first lecture on chapter 2 on motion, sometimes called kinematics. You should give the chapter a good reading, the sections that were assigned to you. Always work through all of the example problems. They're worked out step for step. Make sure you can get those right answers. And that's usually the best way for you to build your foundation of understanding what is happening in terms of the physics. There's definitions at play, there are physical concepts at play, there may be physical laws at play. You need to understand those things so that you can use them. Being able to use and apply ideas is one of the harder things we have to do when we go to school. And so it's not anything magic that people are born with. It's just a matter of getting practice with it. So one reason that we chose the textbook that we did is that it is filled with examples that sort of build slowly on the mathematical skill level, as well as the use of the concepts and the laws and the definitions. And so read through the chapter, make sure that you are picking up key definitions, and I'll be pointing some of those out here today. As well as being able to use those definitions and those concepts mathematically to be able to make predictions. Because science, especially physical science, is really about the idea of being able to make predictions based on some information that you do have. So as you start taking a look at chapter 2, there may be a lot there that doesn't have a lot of meaning to you. Just like if I were to look at something like this, it has no meaning to me. I'm not practicing this. I know that it's some sort of musical notation, but somebody who's well practiced, that notation tells them exactly where their fingers are going to go on a keyboard, for example, and at what tempo they're going to play and so forth. But people aren't born at that. You have to kind of be able to get to that point. So this right here is this is the language to the musicians. What you start seeing in your textbook is a language that the physicists and the physics community uses. And that's something that you're going to have to deal with, and you're going to have to make sure that when you see symbols, that symbol has a meaning to you. So when you look at musical notation, a certain symbol on a certain staff line means, well, your finger is going to hit a certain note and so forth. So everything has meaning here. So it does take some time for you to wade through that and to make sure that that is making sense to you. Okay. So I'm going to share my screen here with you such that I can jot down a few key ideas, and you can take a look and make sure you're getting some notes on there, and then make sure that your notes are matching up with some of the important ideas you're seeing in your reading and in working through those examples. Always work through the chapter and the examples before you try to tackle your homework assignment. So your homework assignment is something that's already been given to you, and they are problems out of chapter 2 and questions out of chapter 2. If you have older editions, you will find those problems and they just haven't been mixed up. So by me giving you those problems, you don't really have to worry about looking for them or anything like that at all. So that's really sort of the idea. But chapter 2 is really on this idea of motion. And it really is the place where modern physics really starts. And really the key character here that gets us started is going to be Galileo. And the time frame that we're talking about is probably around 1600 or so. Now, other people have done physics before Galileo, but for the most part, it was really based on intuition and maybe some observation and so forth. But Galileo is really a key character here. He might be sort of the right person at the right time, really doing the right thing. He's going to have a hard job. He's going to have to undo the physics that already exists to the thinkers of the day. So 1600, either you're a mathematician, you're a natural philosopher, maybe you're a musician, Maybe you are a religious expert and so forth. And but people did have some physics, and the physics is really coming from about 2,000 years before that from Aristotle. And Aristotle is going to make physical statements about the world that we would call laws today, mostly based on observation and intuition. And we have found just about every time in human endeavors that when we use our intuition for scientific purposes, we're usually wrong. Your intuition is good to keep you alive, but it's not usually a good place to start when it comes to understanding the universe. Galileo does something different than anybody else has ever done. And this is why he's the father of modern science. He starts doing measurements, and he starts taking considerable measurement and doing an experiment, and his conclusions are really going to be drawn from there. And so when he starts debating some of his colleagues, he's not doing so based on the authority of people that lived 2,000 years ago. He's doing it based on his measurement. And ever since, we've been doing science the same way. But to Galileo, if you want to specify, and here we're all talking about an object's motion. You want to specify motion. There's going to be three things that you need to be able to specify. If you can't specify all three, then there's a chink in your armor. There's some knowledge there that you just don't have that you probably need. The first thing to be able to discuss with specificity on an object's motion is its position. Now, to Galileo, position means exactly this. Where is the object relative to where it started? Nothing more, nothing less. Where is the object relative to where it started? We could just write out the word position anytime we want to talk about position, but like musical notation, we have shorthand, and that's part of learning the language and so forth. And your textbook uses a pretty traditional notation, and it works pretty well. To signify where an object happens to be, your author of your textbook is going to use the letter X. So X is essentially like a number line, like the x-axis, and we can have an object that moves back and forth on the x-axis. And where it is on the x-axis is going to be measured from maybe some relative origin, or from where it started, but we're going to always make that measurement in meters. So for us, we've got to use the system that the rest of the world is using, especially the scientific community. We've got to use the system that really comes down from Napoleon, forcing everybody to use, the metric system and so forth. But position is, where's an object from where it started? Now, another word that means essentially the same thing is this idea of displacement. Displacement is a measurement of where an object is from where it started. Now, a word that we use in our everyday language that means something a little bit different, even though sometimes it'll mean the same thing, is this idea of distance. Distance, typically, in general, is not the same as position or displacement. So, let me give you an example of where they're the same and maybe where they are different. So let me just kind of maybe scribble something down here. So for example, let's say we've got something that can move on this number line, and the number line is being measured in meters. And let's say that it starts right here, and this is the 1 meter mark. And there's the object, and it's going to end up down here. At some other location. So it's going to go here. So it's going to go at the 1 meter mark, and it's going to go until it hits the 3 meter mark. Okay. So what is the distance that the object moved? Well, the object moved 2 meters. it moved 2 meters to the right, or it moved 2 meters in the positive x direction. The position of the object is at the 3 meter mark. That's what Galileo means. Where is it from where it started? Well, you could say position is 2 meters to the right of where it started. You can say its displacement is 2 meters to the right where it started, and that it's, so in some ways here, the distance that it moved, 2 meters to the right, is maybe the same as the change of position, 2 meters to the right. But the position is actually 3 meters on the number line. So they are slightly different ideas. The place where they become the same idea, that is, you will always get the same answer, and why a lot of times the word distance and position are interchanged in our everyday language, even though they mean something completely different to the physics community, is if you have an object that moves on a number line, if I can get a number line to be drawn here, and if it starts at the origin, so if it starts at x equals 0, and maybe it ends up here. So it moves from the origin, moves, and it stops at the 2 meter mark. Now the distance that it moved is 2 meters. The position is the 2 meter mark. And the two ideas are the same, distance and displacement, or distance and position. But that's really the only time when those two ideas really overlap, is when an object starts at the origin and moves in one direction only. Then they really kind of mean the same thing, but we need to do better than that. The Greeks will be very, very confused over motion and so forth, because they weren't really being specific in their definitions like Galileo's going to be. So he's going to be able to undo a lot of the confusion that they had. For example, yeah, most of you have taken some sort of PE classes and so forth, and you might have to run around the track. Well, how far is it around the track? It seems like maybe around the track is something like 400 meters or something close to that. So give this some thought here. So let's say, for example, you know, the track might be sort of shaped kind of like that. It's got some straight sides to it so that you can have sprints and so forth. And so if you start here at the starting line and somebody runs, you know, all the way around this track, the distance that they have run is 400 meters. However, just as they cross the finish line, their position is 0. They're right back to where they started. Very, very different concepts and so forth. And so we need to be very, very careful that when we're talking about position, it's not always the same as distance. So there is some overlap, but in general, they are not always exactly the same. I don't know if we're going to have a football season this year or not, but we're getting close to the football season. I know that there are 11 players on each. Let's say that we've got you know, the offensive line here, and here's the football, and here's the quarterback, and here's the running back, and then there's some defensive linemen that sort of sit on the other side of the ball. And you know, I'm not going to draw all 11 of them, but the football gets hiked to the quarterback, and the quarterback then pitches the ball back to the running back who just disappeared on us. So the running back gets the ball, and he's supposed to sweep around the edge here, and he finds out that, oh, there's a bunch of guys over here that are in the way. So he turns around and he runs all the way back, and then he turns the ball upfield and he gets tackled right here. And the referee picks up the ball and then puts it, you know, kind of like right up here. And now at the end of the season, the running back, you know, maybe negotiate a new contract, and then he may go to the general manager and say, hey, you remember that run when, supposed to sweep left around the line and, there's a bunch of bad guys there. So I turned around and went upfield. In that run, I ran 40 yards for you. And he might have run 40 yards. And I don't think the general manager is going to be too impressed with that. He's going to say, you didn't run 40 yards. You got me 1 yard. The ball started here. It ended up there. And that's the net displacement. So very different ideas. The ball player did run all this distance, but the ball gets placed right here. And so its position is 1 meter upfield from where it started. So position and displacement mean the same thing, but they are typically different than what we mean by distance. Okay. So now, if an object does not move, its position does not change, and it's pretty simple motion to analyze. It's a done deal, right? The position is its starting position, it never changes and so forth. And that's not a very exciting world that we live in. So what we need to do is allow objects to be able to move. So that's what we're going to do. So let's let objects move. And so if an object moves, then we have a second concept. Remember Galileo, so there are 3 things we need to specify when it comes to an object's motion. The second one pertains to the object being able to move, and he's going to call that velocity. Now, instead of writing out the word velocity, most of the time we're going to use a shorthand notation, and it's going to be the letter V. And I am going to probably put a little arrow on top of that to tell us that it's a special type of number. That direction is going to be important too, and eventually we'll call that a vector. And to Galileo, in words, this velocity is the rate of change of an object's position. Velocity is the rate of change of an object's position. That's something we need to memorize. Velocity is the rate of change of an object's position. We need to know those words, but those words do tell us exactly what to write down mathematically. Velocity is the rate. Any sort of rate is something being kept track of per time. So per time. Velocity is the equal sign per time of a change of position. So maybe I'll write this out. Change of position. Velocity is the rate, something per time of a change of position. And there's no reason why we can't write it this way. We just don't. We always have a shorthand notation, and so this is always part of what a student has to kind of cope with is what does this notation mean? Now a change, we're going to use the Greek letter delta. It looks like a little triangle. That signifies a change in position is an X, and it's going to be, once again, one of these special type of numbers, a vector. So I'll just put a little arrow on top of that. In time will just be the letter T. Velocity is the rate per time of a change of position. If there's no change in position, there is no velocity. Now the change in position, we already said the position will be measured in meters, so a change will be measured in meters, and time will be measured for us in seconds. So this is a definition that really we memorize. This is something that you know as a student. You can't go through chapter 2 without knowing these 3 main concepts of position, velocity, and there will be a third one here in a moment. Okay. Now, once again, we have a word in the English language that is very close to the word velocity, and we use it interchangeably quite often. So much so that sometimes we think they're the same thing, but there are some nuances there which I'll give you some examples to show you that the idea of speed and velocity are not exactly the same. So for example, if, heaven forbid, someday you've got to drive to Fresno, And we say it's 100 miles to Fresno, from Modesto to Fresno. And it takes you 2 hours. Okay, 2 hours to go 100 miles. There's already a number in your head of how fast you happen to be going. And what pops up in your head automatically is this idea of 50 miles per hour. Now, what you just did in your head is really what we call an average speed, which is not exactly the same as a velocity. So it really is a different concept here. But the idea of an average speed, and a lot of times your textbook will write that, and he'll put like a little AV here, or just a straight bar, but it's really the total distance that something has gone divided by the total time that they were traveling. So the total distance you go to Fresno, 100 miles. The total time, 2 hours, one divided by the other, you get 50 miles per hour. And so that is your average speed. And in this case, your velocity may or may not be that number. If you have cruise control on exactly at 50 miles per hour, and it's a straight shot to Fresno, then the two numbers and the two concepts overlap. They are exactly the same thing. But for the most part, there's probably some twists and turns in the road. And so your position is changing into different directions, which is the little arrow over velocity and over position. That's what it means, is your direction changing. So if your direction is changing, then it's not going to be the same as average speed. Average speed does not take into consideration which direction you're actually moving in. So they could be the same thing, but only if you're going in a straight line at constant speed. Then your velocity and your speed will be exactly the same number. So let's go back to the idea of you running around the track, around the football field. So let's say it takes you, a world-class runner can run a mile 4 times around the track in 4 minutes. So that's 1 minute per lap. So let's say it takes you 2 minutes to go around the lap. So you go around the lap and it's 400 meters and it takes you 2 minutes or 120 seconds. And someone asks you to do this calculation of what is your average speed. And so you've got, for example, you've got my average speed is I went 400 meters and it took me 2 minutes, so that's 120 seconds. And so I'm just going to get my calculator out and say 400 divided by 120, and it tells me 3.33. And at 400 meters, I think that's probably to the nearest meter. So maybe I'll leave something like this. So for a person that takes 2 minutes to go around the track, they're going about 3.33 meters per second. Okay, now, just as they start here, they run around the track, and just as they complete it, that's when we really hit the stopwatch to get the time. What is their change of position? Well, they're back to where they started. Their change in position is 0. Therefore, their velocity is 0. So your average speed is not the same as the velocity of the object. Just as the object crosses the finish line, the velocity is going to be 0. And you go, well, how do we really get 0? Well, velocity is the change of position over time. But just as you cross the finish line, you're right back to where you started. Your position at that point is not changed at all. And it took you 120 seconds. And so at that point, your velocity is 0 meters per second. So there are different concepts, but they do overlap. Once again, if you're going in a straight line at constant speed, then your velocities and your average speeds will be the same. But in general, they're not. So we need to make sure that we're paying attention to this. And this very idea of average speeds and velocities is really what confused the ancient Greeks considerably. So much so that some of these very, very smart people that lived over 2,000 years ago, not only were they confused about motion, Zeno of Elia, there's a couple of Zenos that will be running around in your philosophy classes. Zeno of Elia actually makes very, very cogent arguments that motion is impossible. And you might think, well, that's sort of an odd thing to say. We see things move around us all the time. Why would you, sort of come up with this idea that, you can't move when we sort of see things move? And, someone like Zeno would probably be astute enough to say, well, if you've ever stuck an oar down into the water on a rowboat, the oar at the surface of the water looks like it's disjoint. And you get the same sort of idea when you put a straw in a clear glass with a clear liquid. It looks like it's maybe, disjoint here a little bit. And we really don't think the straw is broken or anything like that. But our eyes are telling us that the straw is kind of funny shaped now, and so forth. And so Zeno would be, trying to tell us that, we'll see, your senses are not always the best guide to your understanding of the universe. Your sense lie to you. So what is there that is always going to tell you the truth? And Zeno's going to put his money on something like mathematics. And so Zeno's going to say that, things can't move because the mathematics dictate that. And so he's going to give you some sort of argument like this. We got an object that's going to start at point A, and it's going to go to point B. And he says, well, okay, before it gets to point B, it's got to pass through this halfway mark first. And yeah, you have to go from A to B, you got to go through the halfway mark first. And he goes, okay. He says, well, while you're at the halfway mark, to get to point B, you got to go through the shorter segments halfway mark, which leaves, 1/4 the total distance left to go. And he says, well, once you're there, then you have to travel half of that distance to get to B, which leaves, 1/8, 1/8 of the total trip left to go. And then you got to pass through its halfway mark, and you got 1/16 of the total trip left. And you can kind of see this road that Zeno's going down. To go from that mark to point B, you got to go through its halfway mark, and so you have still 1/32, 1/32 left over. And then after that, you've got 1/64, then 1/128, 1/256, 1/512, 1/1024, 1/2048, and so forth. But there's always a little tiny sliver left, right? All he's doing is dividing by 2. He's not doing anything more complicated than that. But there's always this little piece left. The piece gets smaller and smaller and smaller. But Zeno says you never get to point B. He said it's an infinite run. You can never get there. And mathematically, as you divide by 2, you never kind of get to B. So he's got kind of a point. So as you're sort of scratching your head, thinking about that, saying, well, yeah, okay. It looks like I hardly ever get to B. Zeno, he's not quite done with you. He says, well, let's just look at this first part of the trip. If you started at A, did you ever even get to this halfway mark? To get to the halfway mark, you had to go through its halfway point. And then he uses the same argument that you never reach the halfway mark because, you kind of keep dividing things by 2 and so forth. So if you can't get to the halfway mark, eventually he backs you all the way up to point A, and he says, look, motion is impossible mathematically. And someone like Aristotle 2,000 years ago is going to look at these arguments, and he's going to essentially say, well, Zeno may be, very, very rational, and this may be true mathematically. However, I see things move, so I'm not going to maybe really kind of worry about some of these sort of insane little arguments and so forth. And Galileo is just going to basically go by with what he can measure. And we measure things moving, and so that's just the way that we're going to kind of proceed, much more of a practical sense and so forth. But this idea of your velocity and your average velocity, or average speed is actually a better word, are different. And so we need to take that into consideration. Okay. This leaves us the third concept. And the third concept that Galileo says that we must specify objects' motion with precision is this idea of acceleration. In words, acceleration is the rate of change of an object's velocity. So Galileo is going to allow an object's velocity to change. So acceleration is the rate that an object changes its velocity. So we probably don't want to write out the word acceleration all the time, so we're going to have a little shorthand notation for that. And that's going to be the letter A. Acceleration is equals the rate, something per time of a change of velocity. Those words we memorize. Acceleration is the rate of a change of velocity. Those words tell us to write down something like this. Acceleration is equals sign the rate per time of a change of velocity. Now, a change of velocity will be measured in meters per second. Time is going to be measured in seconds. And so what you end up with is meters, and you have seconds times seconds really on the bottom of that fraction. And so we get something like this, meters per second squared, or sometimes people will read this as meters per second. The way that I really like to think about this is meters per second per second. It tells you how many meters per second, maybe your speedometer, if you have an old needle speedometer on a car, is changing per second. So if you have cruise control on and the meters per second are not changing, you always have the same speed, this acceleration is 0. So the acceleration is really a measurement of how fast that needle in the car is changing, or how quickly the numbers are changing. So usually in your car, you know, the numbers change, you know, just kind of gradually. If you're at a stop sign, you're going 0 miles per hour. And then it's your turn to go, and you proceed, the numbers start picking up. How fast they're changing is exactly what acceleration happens to be measuring. Now, 400 years ago, Galileo probably does not have a lot of things that are accelerating to you know, great numbers and so forth. There's no cars, there's no airplanes, you know, and so forth. And so the mythology is that Galileo is dropping cannonballs off the Leaning Tower of Pisa and so forth. And his notes actually say he's doing exactly that. So see, I think he's got some graduate students up there on the top of the tower, and they're dropping things, and he's doing the best he can to time them and so forth. And he's going to find out some interesting things by some very simple experiments, but with some very careful measurement, and looking at those measurements, he's going to understand something very, very deep about nature, and eventually that'll become our first law of motion. But this idea of acceleration is probably the one that you are least familiar with when it comes to the 3 big ideas, the 3 concepts when it comes to specifying an object's motion. So you've got position, you must specify, velocity, and acceleration. Now, this acceleration is a vector. That is, it's a number. It's also a direction. So let me give you an example of what that direction means, and maybe how to kind of make sense of this and so forth. So let's say, for example, we've got you know, a very elaborate drawing right here. Maybe I've got a car here, and it's at the stop sign. Okay, and so it's not moving. And it's going to accelerate. So once it's the car's, you know, the driver's turn to go, you're going to step on the accelerator, and the car's going to go faster and faster. And so my notation is going to look something like this. V0, that little 0 down at the bottom means V times 0. So there's some of the notation. This car is not moving. But then it's going to accelerate, and let's say that it accelerates at 3 meters per second per second. What that means is that after stepping on the gas pedal for 1 second, this car is now going 3 meters per second. In other words, I added 3 meters per second for every 1 second that the car is traveling. So after 2 seconds, this car is going to be up to 6 meters per second. I'm going to add 3 meters per second, because that's what this says. It says add 3 meters per second for every 1 second that the car is traveling. So this is an acceleration. That's the word that we would use. And a lot of times we don't put the little plus sign there. We just default that it is a positive acceleration. That is, the object is going faster, faster, and faster. And so you can see, as long as the person keeps this acceleration rate up with the gas pedal, you know, in the next second, after 3 seconds of traveling, you're up to 9 meters per second, then you're up to 12, and then you're up to 15, and so forth. You're just going to keep adding 3 until the foot on the gas pedal changes and so forth. But in everyday language, we have this idea of a deceleration as well. So let's say you see this car and it's going 30 meters per second down the road, and the driver sees there's a stop sign up in front, and so they're going to step on the brake, and so there's a deceleration, and so we're going to say we're going to subtract from your starting speed, and maybe we're going to decelerate at 5 meters per second per second. And so what that means is, when I first see the car would be clocked with a radar gun at 30 meters per second, but at 1 second, the car is down to 25 meters per second. So I'm going to subtract 5 meters per second for every 1 second of time. So after 2 seconds, this car is down to 20 meters per second. I'm just going to keep subtracting 5 meters per second for every single second. And so obvious questions that start showing up at the back of chapter 2 in your homework assignment and so forth would be, well, the car is going 30 meters per second when you first see it, and you have a deceleration rate of 5 meters per second. How long, time-wise, does it take for the car to stop? And so you just keep taking 5 away until you actually hit 0. And so I think here we're going to say something like 6 seconds, right? I don't need any sort of fancy mathematics to see that this car is going to take 6 seconds to do a complete stop. Now, Galileo doesn't have the luxury of cars and that sort of thing, which I think is one of the reasons why he's probably dropping balls off the Leaning Tower of Pisa, and he's trying to make some measurements and so forth. Because when you drop an object here on Earth, it accelerates, and it accelerates at a constant rate. So intuitively, you do know this. So if you're standing on the top of a table that's maybe 3 feet off the ground, about 1 meter off the ground, if you jump off that, you're falling for a very small amount of time. So you did not have that much time to pick up speed, but you were accelerating. So you're standing on the table, and you're going 0 meters per second. As you step off, when you hit the ground, you're going faster than 0 meters per second. Now, if you're 2 stories up and you know that you step off, you're going a lot faster than you were off the tabletop, because you're going to pick up speed and you're going to go faster and faster and faster. So Galileo is studying that motion with some very precise measurements. And some of our experiments this semester, you won't be able to do them yourself, but we'll look at some of the data. We'll go down that line of being able to see exactly what Galileo was looking at. But a falling object on Earth accelerate, and we call this free fall. This is an object falling just under the influence of gravity. We're not worrying about air resistance or the wind pushing it or anything like that at all. So once you let it go, it starts from zero, and then it picks up speed. So, if we imagine Galileo sort of, doing this experiment up here in the Leaning Tower, and he's got his, little cannonball right here, and it starts with a speed of 0 meters per second. I don't know how fast it's going after 1 second or after 2 seconds unless I know that acceleration rate. But this is something that Galileo actually measures very, very nicely in some very clever experiments, because he doesn't have clocks like we do today. He doesn't have exact timing, precision, and so forth like we might. But being very clever fellow, he's able to make these measurements anyway. And so many times we write this as acceleration. We'll put a little g there because it's due to gravity. And on the Earth, it's just about 9.8 meters per second. And for the most parts, I'm going to use 10 because it's close. We're only off by about 2% and so forth. And so as you start working through your homework problems and so forth, if you use 10, that's fine. You won't notice any difference between your answer, maybe an answer in the back of the book and so forth. But something like 10 makes life kind of nice, so that after about 1 second of falling, an object on Earth is up to 10 meters per second. It doesn't tell you where it is or how far it has fallen. That's a totally different question, but it does tell you how fast it happens to be going. So after falling for 2 seconds, the object will be up to 20 meters per second. I'm just going to keep adding 10. I'm going to keep adding this number, because this right here, 10 meters per second for every 1 second of fall. And so after 3 seconds, this object is going faster and faster and faster. But if you hit it with the radar, then right at the 3 second mark on your timer, it's up to 30 meters per second. And so this is the acceleration rate for objects on Earth. Different planets, different moons will have different numbers. People have walked on the moon, and we had to know those numbers, exactly what acceleration rates would be there as well, because that has everything to do with how you're going to design a rocket to land there, how to take off, and how to put it in orbit and so forth. So Galileo is dealing with falling objects as his primary example of objects that speed up and slow down with a constant acceleration. That is, they just keep picking up 10 meters for every single second that they fall, as long as we can disregard any sort of air resistance and so forth. So this is a good time for you to probably sit back, maybe hit pause, and remind yourself that there are really 3 concepts here that we need to keep track of to be able to specify an object's motion: the object's position, velocity, and acceleration. Position is, where is the object relative to where it started? That's measured in meters. Velocity is the rate of change of the object's position, measured in meters per second. Then the third concept, acceleration, is the rate of change of the object's velocity, measured in meters per second per second. The words are great and so forth, but it's probably time for us to take a look at, how the mathematics starts playing into this and so forth. So let's take a look at the definitions here and probably start there. So let me kind of start at a new page here, and I'm going to kinematics. Kinematics will be our mathematical representation of how an object's move. It tells us exactly what it's doing at a particular point in time. And really, to start with kinematics, we just start with this definition of acceleration. Acceleration is the rate per time of a change of velocity. Now, a change means that there is something different now than what was happening before. So a change is a difference of where it started at time equals 0 to some, we put a little f there, some sort of final time. That is, you have an initial velocity that's going to change. You might have your foot on the gas and you're speeding up, but you started from a certain number and now you're going to be traveling for a certain amount of time. We want to know what that speed happens to be later on down the road. So you have a final velocity. And so a change is always get what you have now, your final state, subtract off what you had before, and that's the difference between those two numbers. So that's what a change always is. What you have now, subtract off what you had before. And that's how we figure out a change. Now, if I just happen to live in some world where I don't like fractions, I'm going to multiply both sides by t. And I have AT here, and the other side I would have my change in velocities like that. And then I'm going to maybe get this initial velocity here, and it's being subtracted on this side of the equation. I'm going to put it on the other side of the equation, and then just rewrite the whole thing this way. Now, what is this? This is really nothing more than the definition of acceleration, just with some steps of algebra to write it in maybe a little different form, but all the same information happens to be there. I'm going to refer to this as our first kinematic equation. And it's really just the definition of acceleration. Okay. This is an equation that a student will memorize. You'll want to know this. It only took, 20, 30 seconds to get it from the definition of acceleration, but it's important that you have this and you start kind of working through your homework in chapter 2. You're going to have this right in front of you, and once you use it over and over again, eventually you're going to have this memorized. But for something like quizzes and so forth, yeah, you want to have this just at your fingertips. Now, units that go in here, and the units have to really kind of make sense. So, there's quite a bit of talk in chapter 1 about units and so forth and dimensional analysis. But this acceleration has to be in meters per second per second. Time is measured in seconds. There's a plus sign here. This velocity is in meters per second. Now, there's an operation being done here with units, but if I take a look, this second bottom, so what I have here is meters per second from this term plus meters per second, and meters per second plus meters per second is meters per second, which is exactly the units of a velocity. So that's what we want to see. If I put the right units in, it's going to always calculate the right units. So that's our first kinematic equation. The second kinematic right now is a little bit of a mystery to you where it comes from. If you know some calculus, sometime I can show you exactly where it comes from. And Newton, who's going to develop the calculus, he'll be the next generation physicist after Galileo, will be able to derive this. But Galileo knows that this is true. He knows that your change of position equals your rate times time. So you did a number of these problems when you were in 5th and 6th grade, and they say something like a car is going 40 miles per hour and is traveling for 3 hours. So how far has it gone? And so you go, well, I'm going to get how fast it's going, distance equals rate times time, multiply how long it is, and out comes the answer. And that has to work. So Galileo knows that this needs to be true, but this is the starting speed. So if an object accelerates, it's going to have a second speed as well, and many different speeds as it, before we look at the final time and so forth. But if an object does not change its speed, it's not accelerating, this tells us the truth. Position equals rate times time. This is true with no acceleration. So there must be a piece here that has acceleration in it, so that when acceleration equals 0, that piece of the algebra dies off, okay? But we have to look at units. So this is in meters per second, but eventually on the other side of the equal sign, I have position, which is just meters. I need to get meters per second to give me meters, just like this first piece does, right? This first piece, velocity is in meters per second, and time is in seconds. Those seconds cancel, that leaves me with meters. The second piece has to calculate meters as well. So I need to get seconds squared here to cancel out. So Galileo knows that I need t squared right there. And for the most part, in terms of dimensions, dimensionally, this is correct. This works. But his experimental data tells him that this is not right. This will not give you the right answer for an object's position and is moving under a constant acceleration. We need a 1/2 right there. So for Galileo, that 1/2 is a result of doing a lot of very, very clean measurement and knowing he needs that 1/2 right there that has no units or anything like that at all. But that 1/2 will give you the right answer. Newton will be able to tell us exactly where that 1/2 comes from and so forth. But, when you were in 5th grade, the second piece here, this 1/2 AT squared, did not exist because you were not allowing the object to accelerate. So the acceleration was 0. So when you multiply by 0, that whole piece dies off, and it leaves you with the familiar change of position equals rate times time. Okay. I'm going to always refer to this as our second kinematic equation. Okay. So right now, this is experimental data from Galileo. Eventually, we need a third one. And with the 3 kinematics, we can do a lot of damage when it comes to talking about an object's position and so forth. And an object's velocity and an object's acceleration and where it happens to be and so forth. That is, we'd be able to specify anything about the object's motion. We're just missing, like when I look at this kinematic right here, I see no final velocity. So I don't see final velocities connected to position, for example. When I look at the first kinematic, I don't see position there at all. So there are some concepts that are not linked mathematically yet. So this is why we need really this third kinematic. So let's take a look at third kinematic. And I'm going to start with probably there's many ways of doing this, and your textbook will do this as well. But let's do this. Here's our first kinematic. Final velocity equals initial velocity plus acceleration times time. And I'm going to solve that kind of quickly here for time. That is, I'm going to try to isolate the t. So in doing so, I think what I would do is get that velocity and that initial velocity, subtract it from both sides, and then I need to divide both sides by a, and I can solve this for t, and there's no new information there. I just sort of rearrange this thing mathematically. So I'm going to have it kind of in my back pocket here. Now, if something that we happen to know is true, for example, that change of position equals, say, for example, an average velocity times time, and maybe my average velocity, I can get my final plus my initial. divide them by 2. That's a way to kind of come up with this average here, times time. What I'm going to do is get all of this stuff right here, all of that garbage. I'm just going to stuff it in that spot for time. So in other words, just kind of eliminate time from this completely. And this is going to give me a combination of concepts here that I don't already have in the other two kinematics. And so you might look at it and go, uh-oh, on the top you have a binomial, which your math teacher is going to refer to it as, times another binomial. And so this is, okay, I've got to FOIL this, right? First, outside, inside, last. And so I'm just going to use the rules of algebra to sort of do this. So my first terms, first I'm going to get a VF squared. Inside, outside. Looks like I get something like this. And then lastly, I'm going to get those terms. And then on the bottom, 2 times A is just 2 times A. So it looks like the cross terms here cancel out. And I've kind of got what I want. I've got velocities, the starting and a final. I've got acceleration. I've got my position now too. So I've got a position now connected to velocities, but I don't really have totally all that information in my other kinematics. So if I do a couple steps of algebra here, I am going to end up with this. And I'll probably refer to this as my third kinematic. So the 3 kinematics, start with, you want to have those right in front of you as you are trying to work through some of the questions and problems in chapter 2. And eventually you will have these memorized. So when it comes time for quizzes and so forth, you just want these at your fingertips, okay? So there are the 3 kinematics. These are 3 mathematical relationships that must be true for an object that is accelerating at a constant rate. The 3 kinematics are only true if there is one number, and one number only, that you can plug into for A, for acceleration. Acceleration must be constant, which is why it works for things like falling bodies and so forth, because the Earth, near the surface of the Earth, has just one rate that it happens to accelerate objects and so forth, this 9.8 meters per second per second. So the kinematics are true, but acceleration must be constant. So something driving in your car where you're speeding up and then hitting the brakes, slowing down, that already is more complicated than what the kinematics can handle, unless we do it piece by piece. We can do maybe the speed up if you have a constant acceleration. We can do the slow down with kinematics, but you can't do it all at one time if there's a change of accelerations and so forth. Now, in your package of stuff, you should have a number of examples and so forth. So let me see if I can't kind of pull this up. So yeah, so in your package of stuff, maybe on, looks like page 7, we've got something that says examples of 1D, one-dimensional motion. So these objects are just moving in a line. We can allow them to stop and turn around and those types of things, but it's just linear motion for right now. Eventually, in the next chapter, we'll allow the motion to get more complicated and so forth. Now, to handle any of these types of questions, I really want to have probably about 3 things going for me. I want to have the definitions at my fingertips: definition of position, velocity, and acceleration, and what those mean in words. Position, where are you from where you started? Velocity, the rate of change of position. Acceleration, the rate of change of velocity. I want those definitions. Something to help you with the calculations, have just some sort of calculator with you. And the 3 kinematics at this point should be sitting right in front of you. So even if you write them off on a card to the side, you really want to have those because most of the time they will be able to answer the question usually in one step. So sometimes not. Sometimes we have to be more clever, but a lot of times that's true. So as I take a look at this first example here, it says a racing car starting from rest. That's already telling me something. So when I read that, starting from, that tells me something with my notation. Starts, that's the starting speed. Starting from rest, the starting speed is 0 meters per second because it says it starts from rest, okay? It says it accelerates at 5 meters per second. What is the velocity of the car? That is, find the velocity at some later time. So that time happens to be at 6 seconds, okay? And what they're asking for is, what is this final velocity? So those words really translate into these symbols. So remember, this has got to mean something to you, right? The symbols have got to mean something to you. And that's part of kind of working through this. So those words are telling me, in terms of symbols, this is what I've got going. What's the velocity of the car at t equals 6 seconds? In other words, what's the final? Look at your kinematics and see if you can't find one that will give you an answer essentially in one step. In other words, you're looking for one of those that has everything in it that you need to know except for final velocity. And if you take a look at those, I think maybe this one is the one to try. It's set up for what is the velocity of the car at t equals 6 seconds. So my starting speed is 0 meters per second. My acceleration is 5 meters per second. I'm going to let the object travel for 6 seconds, and that's it. So in other words, it starts from 0 and it picks up 5. And we're going to let it do that for 6 seconds. So after 1 second, you're up to 5. After 2 seconds, you're up to 10, and then so forth. So after 6 seconds, you're up to 5 times 6. And you take a look at the units, and you're going to get 30 meters per second. So it kind of looks like here that everything is like 3 significant figures. So I'm just going to match up with that and leave my answer here in terms of 3 significant figures. But that's always the game. Have the kinematics in front of you and then translate what those words mean in terms of the symbols, and then see which kinematic is going to help you solve the problem, that is, answer the question. Part B, what is the velocity of the car after it has traveled 100 meters? So now I'm looking for a velocity, not at a time on my watch, but at a certain place, at a certain position. And so what's kind of coming to my way of thinking here, looking at this problem, is maybe the third kinematic. At a later time, that is a final velocity. I know the starting rate, I know the starting speed, it starts from rest. I know the acceleration, and I happen to know where its position happens to be. So everything here is moving in a straight line. So I don't have to worry about any nuances or anything like that here at all. So it starts from rest. That 2 is always built in. The acceleration of this object is 5 meters per second. And it happens to be 100 meters from where it started. And so I think that's it. That's one equation, one unknown. That kinematic has all the combinations of those concepts built into it, where it will tell me exactly the answer. Now, you have to remember, this is v final squared, so eventually we're going to have to take a square root and so forth. But as long as I don't make a mistake here algebraically, 2 times 5 is 10. 10 times 100 is 1,000. So that's v squared, so 1,000, and I'm going to square root that, maybe 31.6 or so. So verify your calculator that you can get something pretty close to like 31.6. So after it has traveled 100 meters, if you hit it with a radar gun, the radar gun is going to measure out 31.6 meters per second. So the kinematics are very powerful. The 3 of them should take care of just about any situation. Your textbook does have a 4th listed at times, but most of the time you can get by with just these 3. There's usually not a need really for the 4th one at all. But this is always the idea of using the kinematics. So Now let's take a look down here at this next one. So the second example. A car manufacturer claims its sports car will accelerate from rest to 87 miles per hour, mph, in 8 seconds. So already I have a bad feeling about the units here. We're going to have to take care of the units. Determine the acceleration of the car. Okay, so it starts from rest. So I know the starting speed, and I know the final speed, and I want the acceleration. Okay, so I think what I'm going to do is write down exactly what I know. Starts from rest. 0 meters per second. Its final speed, it gets to 87 miles per hour. 87 miles per hour. Okay. I can't mix and match meters per second with miles per hour. So this is the time to look in the front of your book. You're going to have some conversions there. The front of your lab manual has a number of conversions. These are pretty common conversions. After a while, you'll probably memorize them and so forth. But I'm going to get rid of hours and I have to change this into seconds. So I'll get those hours to cancel out. 1 hour has 60 minutes, but each minute has 60 seconds. So it's 60 times 60. 3,600 seconds. And it's close, but a mile is 1 time around the track, 4 times around the track. And each time around the track is about 400 meters. So this will be pretty close. 1,600 meters is about 1 mile. So I'm going to change that final speed of 87 miles per hour into meters per second. And looks like everything here is 3 significant figures, so I think I'm going to match up with that. And on my calculator, when I get 87 times 1 times 1,600, and I divide it by the 3,600 on the bottom, I'm getting 38.7 meters per second. Okay, so it took me a little bit of time to translate, my final speed into the right units, but that's okay. And I want to know the acceleration of the car. The acceleration of the car, and I happen to know how long time it's been going for. This looks like a good case for the first kinematic. My final speed is 38.7 meters per second. My starting speed was 0. I'm looking for acceleration, and the time that it's been traveling is 8 seconds. So there is the physics. The physics is done. Now it's up to you and a calculator to be able to get the answer out. So I've got 8 times A equals this 38.7 number. So I'm just going to get that number divided by 8. And looks like it's pretty close to 4.83 meters per second per second. That is the acceleration rate of this car. Okay. Part B. What distance will this car travel in 8 seconds? Okay, so if it's traveling in a straight line, I could use the word distance. Otherwise, I would like the word position there better. What distance will this car travel in 8 seconds? I think I'm going to use the second kinematic here because it's set up for a change of position. And I happen to already know a lot about this car. Its starting speed is 0. And so that whole first piece dies when I multiply 0 times anything. So I get a 0 there. This back half has got that built-in 1/2. I just found the acceleration rate. So I'm going to put that in for A, and it's traveling for 8 seconds. Only the 8 has the square on it. So I've got the acceleration rate in my calculator already, so I'm going to multiply that by 8 squared, which is 64, and then cut it in half. All right, so I already messed that up. So to 3 significant figures, maybe I'm looking at 155 meters, something like that. So definitely take some practice using the kinematics, but it's not a terrible game that you're playing here. So have the 3 kinematics sitting in front of you. Know your definitions of position, velocity, and acceleration. Know what kind of units that you're working in, and then just go slowly and translate the words that you are given. And usually it'll tell you that there's a kinematic that will answer the question. Usually you can do it in one step, but I'll look at some examples on our next lecture where maybe it's a little bit more complicated mathematically, and maybe we have to use more than one kinematic and so forth. Okay, so that's enough for today. So this wraps up the first lecture on chapter 2. So make sure you start reading the chapter and working through those example problems first. Build up your foundation of understanding. Then once you feel pretty good with being able to work through the examples in the book and get the same answers, then start working on your homework and so forth. And then also use our lecture notes and use those as final checks and so forth. Okay, so so until I see you again, take care, and so I'll see you next time with the second lecture on chapter 2.